Hi everybody. Today we're going to start talking about series circuits, which is one of the two ways of setting up your circuits so that they can follow Ohm's laws. And we're going to be relying mostly on page 4 of our reference table here, our laws for series circuits, which are going to be on page 4 there towards the bottom, and the circuit symbols. And most of the diagrams I'm going to use here involve using these circuit symbols. So what we're going to talk about here is our series circuit. And I'm going to let Jimmy out real quick. Oh, no, Jimmy's running around. All right, so let's take a look at series circuit. Let's see what we are dealing with in this scenario. In a series circuit, you have all of your resistors. They're all along the same wire. What that means for us is we could have a battery here, and I'll draw a battery like this, and this is how they are on page 4. Let's say this is a 12-volt battery. And then we can add multiple resistors, and I'm going to put 3 here. And these are how your resistors look, and resistors can be, let's say, a lamp or really anything that causes electrical resistance. And I'll attach some values for these resistors. So let's say this one here has a resistance of, let's say, 3 ohms. We'll put the next one here with 2 ohms, and our third one with 1 ohm. And we'll call them R1, R2, and R3. If you notice, they are all along the same wire. There's no branching off. If they branched off, that would be what's called a parallel circuit, which we're going to cover in our next lesson. So we have our series circuit here. Notice how it's all going to go through every single resistor. The same current that is pushed through by this battery, the same current will pass through every single one of these resistors, 1, 2, and 3. Because the same current will pass through all 3 of our resistors, well, we can figure out our first rule of series resistors. And our first rule of series circuits, in a series circuit, our first rule is that the current is the same everywhere. In a series circuit, the total current in the system is equal to the current through the first resistor, which is equal to the current through the second resistor, and so on. Our current is the same everywhere. So that's our first big rule we want to keep in mind here, that in series, current, same everywhere. That's going to be our first big rule. Current is the same everywhere. So if I put an ammeter here, or if I put an ammeter here, they would both say the same thing. And here they would both say 2 amps. And we're going to look at why that's the case in a second. So current, same all the way throughout, everywhere in it. Our next rule for series circuit. The current passes through every single resistor. So to find what's called the equivalent resistance, or our total resistance in the system, our equivalent resistance, which is like the total resistance in the system, we simply add up all 3 resistors. So our equivalent resistance is R1 plus R2 plus R3. If we had these 3 resistors, 3, 2, 1, our equivalent resistance of this system would be 3 plus 2 plus 1, 6 ohms. If we had a system that had, let's say, 3 5-ohm resistors, right? 3 5-ohm resistors all in series. So we have a 5-ohm resistor, a 5-ohm resistor, and a third 5-ohm resistor. Our equivalent resistance would be 15 ohms. That's our other rule here. So we could find the equivalent resistance of the system, and you could find our total current in this system. And we're going to talk about that more in a second. Our last rule for series circuits is that the voltage total adds up to the initial voltage. So you can use, oh boy, Jimmy is happy to see everybody. Say hello, Jim. Say hello. There's a quick Jimmy break. What's he doing? Oh. Jimmy, get your butt off the screen. Jim, come on, man. Oh, Jimmy boy. Okay. We're gonna get you out of here. All right, Jimmy wants to be on top of me for this lesson. Okay, you gotta let go. Come on. Oop. Let's go. Let's go. Let's go. Come on. Come on. Come on. Okay. Current, same everywhere. Equivalent resistance, you add up all your resistors. Current is the same everywhere. Equivalent resistance, you add up all your resistors. Good. Now we get to our voltage. And our voltage can be calculated from each individual part here. So let's go into this, and I'm going to start making what's called a VIRP chart, a VIRP chart. A VIRP chart contains our voltage, our current, our resistance, and it's going to also have our power. So let's take a look at a VIRP chart for this. I'm going to make a VIRP chart, V-I-R-P, and we're going to start calculating everything for every part of the system. For R1, for R2, for R3, and for the total system. Actually, I'm going to make this VIRP chart quite a bit bigger here so that everybody can actually see it. I'm going to move our rules a little bit so just to make sure that this all works out. So we have our VIRP chart V-I-R-P for the system. And we want to remember a couple of rules here. We have R1, R2, R3, and the total. That's for the total system. We want to remember a couple of rules here. First one we want to remember, equivalent resistance is R1 plus R2 plus R3. We want to remember that current is the same everywhere. We want to remember that V equals IR as well. That's Ohm's law. And remember, P is equal to VI. Let's use that to build out this VIRP chart. R1, R2, and R3 we can fill in right away. We know those. We have 3 ohms, 2 ohms, and 1 ohm. The equivalent resistance for this circuit is going to be, well, you just add these up, 6 ohms. Our total voltage for the system is 12 volts. That's given here. We don't yet know the individual voltages for each part of the system. We can find our current for the system by doing 12 divided by 6 because V equals IR, so you say 12 equals I times 6, and we can find our current, and our current is going to be 2 amps. Once you have the current is 2 amps here, well, you could say everywhere in the system, the current is going to be 2 amps. And we have 2 amps, 2 amps, 2 amps everywhere in the system. And that's what I put in the ammeters before. Ammeters, of course, measure current. So we have 2 amps all the way through here. Now, we can use that 2 amp current to find our voltage. V equals IR again. So you do I times R, 2 times 3, 6 volts for our first ohm meter. 4 volts for our second ohm meter. 2 volts for our third ohm meter. Notice how we're just doing V equals IR for each part of the system, and you can also do V equals IR for the total system. So you're kind of splitting between part and whole. Notice 6, 4, and 2, what do those add up to? They add up to 12 volts. Our total voltage in the system is equal to V1 plus V2 plus V3. And all of these rules are written on page 4 of your reference table. Let's find series circuits here. I equals same everywhere. Voltage adds up, and resistance adds up. Notice the symbols I'm using here are also from this page of your reference table. Those are your circuit diagram symbols. We will talk about that more soon. Last thing we can calculate here, power. Power is V times I. 6 times 2 is 12 watts. 4 times 2, 8 watts. 2 times 2, 4 watts. 12 times 2 for the whole system, 24 watts. Notice the powers all add up as well. A couple of things I want to note, just a few relationships. Look at the highest resistance here. The highest resistance in series requires the highest power. Highest resistance here requires the highest power to keep the current constant. It also has the highest potential difference drop. The potential difference drop here is how much potential difference you lose in that resistor. It's basically how much your electrical energy gets reduced. There's a reduction in your electrical energy. I also want you to notice that as we have more resistors in series, what happens to your equivalent resistance when you get more resistors in series? Our equivalent resistance will increase because we're just adding them. The easiest way to think of this is like a single lane road. In a single lane road, everybody has to move the same speed, so the current is the same everywhere. In a single lane road, if there's a pothole, it slows down everybody. So if you have a pothole or another resistor, you're going to increase your resistance. So this is like a single lane road. That's your series circuit. All resistors are on the same wire. Current is the same everywhere. Resistance increases directly. And you can make a VERP chart to find any piece of information for the entire system. That's series circuits. We're going to talk about these. We're going to practice with these over the next several days. And then we'll try parallel circuits next. Stay healthy.